So any questions? So what we did last time was we talked about Page's theorem. So since it's been a few days, let me start by restating what we said, sort of the punchline, and then we will use this theorem to talk about the Page curve. Okay, so this is we'll just do a quick recap. Okay, so so the statement is that a generic state. So generic state is something that we spent some time explaining, but you can think of it as some sort of, in some suitably random. So the notion of genericity is usually uses a measure called Haar measure. This is what I explained last time. But you can just, once you can go look it up when you need to, but other than that, you can just think of it as some randomly picked state from the Hilbert space. Okay? So a generic state in HAB, where H is the Hilbert space and A and B are subsystems, and AB is the total system, looks like means in the sense of either entanglement entropy or in the sense of norm. That's what looks like means. Okay, so looks like a coarse-grained what I wrote last time was maximally entangled. Okay, so but what it really means is that it is in some suitable sense, it is kind of like a thermodynamic kind of state. So it was basically, the maximally entangled basically means that once you take the reduced density matrix of the state with respect to, let's say, A, if you trace over A, the reduced density matrix on B is maximally entangled, means it is diagonal. Okay, it's 1, 1, 1, 1. So it's it's the most mixed state. So that's what coarse-grained is. Yeah, I'll explain why I'm also calling it coarse-grained. In HAB looks like a coarse-grained state in HA if the dimensionality of A is sufficiently smaller than B. So this was our statement. Okay, and this is what Page basically proved. This is essentially, he proved it using some Hilbert space technology, like using tensor, like working with finite dimensional Hilbert spaces, and he proved this in various, I don't know whether he proved the most general case or checked it and conjectured. I don't remember exactly now. But yeah, so anyway, this is the claim that he made, and this we know how to prove. Okay, so so the idea here is that, so looks like I already explained, coarse-grained essentially means, so coarse-grained, so there are two kinds of entropy. So we briefly alluded to in the, one of the lectures, I think he had a question and we discussed it briefly, but there is a distinction that we want to make between thermal entropy, which is sometimes called coarse-grained entropy, and what is called, what is it, the von Neumann, or von Neumann entropy, okay, or the entanglement entropy. Yeah, that's a better word. So so that we want to make a distinction between the two. So entanglement, so von Neumann entropy is basically you take a state and then you compute its trace rho log rho. So it's sometimes called fine-grained entropy. Okay, so but coarse-grained entropy is or thermal entropy, roughly speaking, means, so the reason why we are calling this coarse-grained is because if you have a diagonal, if you have a density matrix which is diagonal, it essentially means that you are living in the microcanonical ensemble. Okay, so what that it basically means that there is some regime or range in which you are looking. If you are talking about fixed energy, you can loosely think of it that way, and all the states are roughly equally probable. Okay, so that's roughly the idea. So here, so that's the sense in which you are talking about coarse-grained. And the black hole thermodynamics tells us that black holes have thermodynamic entropy or coarse-grained entropy. Okay, so the statements that we are making about, but now we are talking about, when we are talking about entanglement entropy, we are not directly dealing with coarse-grained entropy, but the connection between coarse-grained entropy and entanglement entropy is basically Page's theorem. Okay, so the statement that he is making is that you can keep track of entanglement entropy of the black hole radiation system as the black hole is evaporating, in certain limits at least. When the radiation, when the radiation is much smaller, in the initial parts, when the black hole is big and the radiation is leaving the system, the radiation can be thought of as a small subsystem. Okay, and when in the very final stages of evaporation, when the black hole is tiny and the radiation is most of the matter is in the radiation, then you can think of as a black hole as a small system. Okay, in both these limits, you can use Page's theorem to connect entanglement entropy to coarse grain entropy. So that's the reason why it's a useful theorem. You see what I'm saying? Because otherwise we don't know how to compute entanglement entropies. Okay, so entanglement entropies of black holes are, like any system, for instance. Entanglement entropy is a very difficult quantity to typically calculate. Okay, if you want to do it, for instance, in a spin system or something, so it's a very difficult thing to calculate. It's an expensive thing to calculate. But the point is that, like, actually one of the things that we will learn, essentially, like slowly we'll get into IISc, is that holography makes the calculation of entanglement entropy easy by geometrizing the calculation in some ways. Okay, so that's a separate fact, but the point here I'm trying to make is that Page's theorem is not talking about the thermal entropy which the black hole directly deals with, but he's talking about entanglement entropy. But the reason why it's interesting is because entanglement entropy, if the system is evolving unitarily, and if your degrees of freedom are leaving from here to here, it should have a generic shape, and that's what we will show now. Okay, so in a unitary system, we can use Page's theorem together with this connection between entanglement entropy and coarse grain entropy to make a prediction about how the Page curve should look. Okay, so this is what we will show now. Okay, so so now let's look at the black hole, evaporating black hole. So this was sort of a recap. Evaporating black hole. How does the entanglement entropy, what is the plot of the entanglement entropy with time? So this is what we are interested in. Okay, so and Page's Page curve is basically the answer to that question. Okay, so I also want to say that this assumes unitarity. Okay, so if black hole evaporation is unitary, then this particular shape should happen. Okay, so that's the assumption, but of course getting it from first principle from a quantum gravity is, we don't know how to do it, but there are mechanisms that we can get now in semi-classical physics, semi-classical gravity, we know how to get it and so on. Okay, so the first assumption that we are making, so let the black hole first, evaporate. Okay, so we are starting with some black hole of some mass and you're evaporating, and the point is that the first assumption that we are going to make, and this is an important assumption, is that at any stage in this evaporation, the state can be assumed to be random in this generic sense. Okay, and that's essentially because we believe that black hole formation and evaporation is an extremely complicated process. Okay, so it's a thermal system. We have some reason to believe it, but if it is not the case, anyway, information will be lost. Because as I said, one of the assumptions about when we did the unroot state in order to make this calculation of evaporation, so the thing that we needed was this assumption. We made this assumption that the state is thermal. So, and the only way we could salvage that situation is by replacing that state by some complicated state, which presumably will behave like, thermal state. It's like a thermal state when you're computing, let's say, scalar field, small operators in that state. Okay, so this is how we are planning to evade the information paradox. So the point is that, so this is what we are going to assume. So at any stage during Hawking evaporation, the state of the combined system, the black hole and the radiation, is always some suitable sense generic in the Hilbert space. Okay, so that's the first assumption. And so basic assumption. The state of state in H R BH. Now I'm calling it radiation and black hole. So that's A and B. Okay. So the state in H R BH throughout Hawking radiation, Hawking evaporation. Evaporation is generic in the sense that is generic, and that's essentially because black holes are complicated things, and by the time it starts radiating, it's some horrendously complicated state in the Hilbert space we have no immediate understanding of. Okay, so that's what this is. So so this is the first assumption. So essentially what it gives you is the possibility that you can you can use now Page's theorem. at each step of the evaporation. Okay, so as I was saying, so if you have a maximally entangled type of state, let's say the assumption in that sense, if when R is much smaller in the initial states of evaporation, as I said, when in the initial stages R is much less than BH. Okay, so in other words, so and it's this log R is basically what the coarse grain entropy would be. But the advantage of coarse grain entropy is that we can actually compute it using what we know about thermodynamics and physics and so on. Okay, so this log R is basically the coarse grain entropy associated with radiation at the initial times, but as the radiation is flowing out, we can actually compute it. It is basically going to be, if you believe in Chethan Krishnan law, it is going to be, so let's make a few assumptions. Most radiation is an S wave, as I said, is an S wave, that means that the L equal to 0 component. Okay, because of the angular momentum barrier, you remember? So, so let's make some assumptions. I mean, anyway, the general shape that we compute will not depend very seriously on it, but you can make this more precise. Page has done this calculation in great detail by taking into account spin, all of these things, working almost with standard model and so on and so forth, with which particles can come out. But essentially, if you just assume massless scalars are being emitted, that's good enough to give you the general argument, general shape. But more importantly, it is only the general shape of the thing that we are ultimately really interested in. Okay, so so most radiation is an S wave, so we can assume that this is a 1 + 1 dimensional Planck radiation formula we can use. Planck radiation or Planck or Chethan Boltzmann or whatever you want to call it, we can use. That means that SR, which let me call it coarse, is proportional to T by M, where this 1 by M corresponds to the temperature. Okay, 1 by M is So the reason why there is T times M is because in D plus 1 dimensions, the entropy goes as T to the D. Okay, for a free gas of radiation. That's essentially Chethan Boltzmann law. Okay, as T cube in 4 dimensions. So see here on the other hand, it's 1 + 1 dimensions, because if you have a spherical shell evolving, it's basically like there is no angular dependence in the problem, right? You're essentially working with a 1 + 1 dimensional problem. Okay, and that's why we have T times capital T is what we have, where capital T is the temperature of the black hole. Okay, so this is how it goes in the early parts, and we know that. So this is basically just the estimate for what the entropy for the radiation should be. And similarly, we also know that just from this is what Bekenstein-Hawking formula computes is proportional to m square. Okay, basically the area of the black hole. Right. So these two are the facts that we know. Okay. So and essentially the statement of Page's theorem basically tells us that these quantities are precisely what the entanglement entropy will be equal to at the early stages of evaporation and the late stages of evaporation. Okay, because at the early stages of evaporation, this is a small subsystem, and at the late stages of evaporation, this is a small subsystem. Okay, and the transition happens at T, as you can see from those equations, as around this thing, and this time is basically what is called the Page time. Okay, so and a second fact we will use is that okay. So this is Page time. So and this quantity. So early parts this part we can fill like this. Okay. So this is starting off like this. We are kind of starting from some 0. It doesn't really matter. It just means that if there is some so you're starting with you can lift it up a little bit if you like. The point is that it goes up and comes down. That's the only point I want to make. Okay, so I'm not really being careful about this end. But the point is, if it starts off linear, okay, And of course our assumption that the small subsystem is valid only when it is really a small part of the thing. So it will start breaking down somewhere when it gets here, which corresponds to a time scale of about page time. Okay, so and after that we will have the other curve which corresponds basically to you will have to use this SBH's m square formula, but we have computed how much time it takes for a black hole to evaporate. I don't know whether you remember it, but it was basically something to the effect that I think it was the T evaporation was m cube, if you remember. Right? So that means that the time at which this guy, so this curve I'll draw here like this is going to evaporate is, so we can write it like this, m square is going to be T final minus T to the power 2/3. Okay? So T is this, and so this is how the SBH will go. Is that okay? So what I'm doing is that I'm fixing my clock at the time when the black hole hits zero mass. Note that, I should be if I'm really being careful, I should say it reaches Planck mass, because then the semi-classical approximation and this formulas all break down, okay? But as we argued earlier, that assumption is not enough to save information paradox anyway. So we don't care. So you might as well assume that it goes, we are not going to specialize to some m Planck here. It's just this general structure is what we're after. So that's the time scale at which that happens. So I'm essentially, when I was computing this formula, T evaporate is equal to m cube, I was thinking of what is the time it starts from. If I had a black hole at T equal to 0, and I computed how much time it takes for it to completely evaporate, the time that it takes is this much. But now I'm setting the clock from here so that I want to understand how this plot looks like. Okay, so that's the reason why this picture, this time looks a little, it looks kind of inverted. Okay, so I'm fixing my clock so that I basically get this to be TF essentially. Okay, so anyway, so the point is it's some 2/3 power, and you can plot it in some shape. The point is even that it is not even important that the shape has this particular form or anything. What is important is that what we, in order to do this, what we have assumed is that the system is, a pure state. So if you have a pure state system, we expect that the entanglement entropy of each of these subsystems is the same, because that's just a thing that you can prove. Okay, if you have a general state in a Hilbert space, and entanglement entropy of the reduced density matrix of A is the same thing as the entanglement entropy of the reduced density matrix of B, if you're starting with a pure state in AB. Okay, you can try it, prove it, whatever, you can look it up, whatever, but it's a fact. Okay, so that's what we have. So these are the couple of things that have gone into our calculation. Is that fine? So this is what is expected if the black hole evaporation is unitary. So the important thing about this calculation is that it's not so much that if you just have two systems in which we basically have one system leaving from here to the other, and entanglement entropy will increase and come back. That's not a very surprising fact. But what is interesting about this calculation is that we have only used semi-classical physics to derive it. Semi-classical physics and the fact that Page's theorem can be used to replace entanglement entropy with coarse-grained entropy. So these are the facts that we have used. Okay, or the third fact you could say is the fact that we are working in the generic state. Okay, so these are the three ingredients that have gone into the calculation. But the most important of them is the fact that we could get this calculation by making statements about the SBH, okay, which we computed using semi-classical gravity, together with general expectations about how unitary evolution should work. Yeah? Yeah, that's the idea.
So after that, what are we calculating the entanglement entropy?
So which time? Sorry?
After T evaporation.
So T evaporation, so yeah, okay, so maybe the confusion is that T page and T evaporation are both order m cube. So here this is m cube, but so these two are essentially in some sense comparable numbers. Okay, so I'm not fixing the coefficient here. I'm just saying that T evaporation is, from our previous calculation, we know it should go to m cube. Essentially, what this time scale determines is how much time does it take for the black hole to change its mass at a macroscopic level. That's what it really measures. Okay, so and if the black hole basically completely evaporates, also it's about the same. But it's like, so that's the sense in which I'm using the same formula here to compute it.
So at page time it has not completely.
It's not completely evaporated. It's not completely evaporated. That's the time when the coarse-grained entropy of the radiation that has left the black hole is equal to the coarse-grained entropy of the black hole that remains. So that's the time that we call page time. So page time is a statement about so the equality of the two coarse-grained entropies. That's what really it is. So note that, I'm kind of, this part is kind of questionable in my approximation.
At page time, both are like
Comparable.
Not one system is small and the other is
Yeah. So small in the sense, in the sense of entropy.
Yeah.
In the sense of coarse-grained entropy, they are comparable. Yeah.
So this model won't work at that time.
That's the reason why this part is somewhat shady or whatever, but it doesn't really matter. You can make it somewhat more precise, and Page's theorem is actually a very good approximation as long as A is even slightly less than B.
How do we know the exact page time if you don't know?
We don't really need to. So we are just trying to understand the general shape of the curve, and the claim is only that by using semi-classical arguments we can get it if you assume unitarity. Unitarity, so the point is that the black hole is macroscopic at all these parts of the curve. So there is no room for quantum gravity to kick in and save you in any real way. If you wanted to do something, you cannot tweak with this calculation without doing damage to what we really believe about physics. That's the point about this curve. It's not so much that, there is some approximation is not as good, etc. So it can take some shape, but any of those shapes doesn't matter. It will still have to go up and come down. That's the point. So the point is that if you just instead, thought of this coarse-grained entropy of the radiation as the only entropy in the system, which is what Hawking's calculation would have you believe, right? Hawking's calculation basically says that the system is always in thermal state. So which means that it will just keep going up and up and up. So that's the page curve version of the information paradox. Okay? So, but on the other hand, if you assume unitarity, okay, so if you just take the state that is given in Unruh's state to be exactly thermal, this is what you would find, because the state is mixed state. There is no purity in the state. But if you assume that the state is pure and you assume that the evolution is unitary, then you are guaranteed to get this back. Okay, and that's what makes this calculation sort of interesting. Okay, so and how do we get this back? In our let's say in our theory, in our classical gravity theory. So the place where classical gravity or semi-classical gravity has gone in is in this semi-classical physics has gone in is in this formula and also in this formula. Okay, this is less remarkable, but in this formula. So here we have used the fact that semi-classical black hole physics and its entropy is valid. So that's what we are assuming there. And in the second, then we are also assuming unitarity on top of that. So that together with this gives you the shape of the curve. And then the claim is, that's basically it.
Have we seen the coarse-grained entropy is decreasing towards the end?
Yeah, because m square is decreasing because of the thing is evaporating, right? So we expect this m square is slowly decreasing, and that's why this TF is TF minus T. Okay, so TF is greater than T. So this m square is decreasing, so we expect it to decrease. So what we have done here is we have made, so the Page's theorem is what kind of made this calculation possible. Because Page's theorem otherwise we would not know how to compute entanglement entropy. But the point of Page's theorem is that if the subsystem is small enough, you can replace the von Neumann entropy with thermal entropy. That's what it gives you. So and then you can make this claim, and then you are left with the particular shape, which Hawking's original calculation cannot reproduce because we are assuming a thermal density matrix. It's not a pure state. So that's the place where this has gone. Okay, so if without this, you will get basically the exact thermal state, and if you wait long enough, the radiation just gets, evaporates, and you get a pure thermal state. Here we are assuming it is pure state all along. Yes, here that's where unitarity is going in. So we are assuming unitarity here, and then Page's theorem guarantees certain, and this formula for entropy is where semi-classical physics goes in, and that's it. Yeah.
When you assume unitarity, you assume
conservation of energy means? We can phrase this question in a slightly different way in canonical ensemble if you want, but it doesn't really change anything.
Yes. So that means you are not taking the system as the black hole itself, but as the black hole and its outside as a whole.
Yeah, roughly speaking, yeah.
Then that implies holography. In the
Why is that? Why does that imply holography?
Because the boundary is at the infinity.
No, I'm just treating. So here, in fact, I'm not assuming holography. If you want to really say that the black hole and the radiation are both, in some sense, holographically described by some system at infinity, that's another possibility. That's, like one could discuss that. But that is not what I'm assuming here. I'm definitely not assuming that at some level, the radiation, the entropy of the radiation, so the system, I'm treating the black hole and the radiation as separate systems, right? So if you have a black hole sitting in flat space and the radiation is leaving the system, and if you assume complete holography in the sense of like everything can be found at infinity, then there is no, then there is no problem. There is no problem, or there is not even a question. Because you have in some sense tautologically solved the information paradox. See, but the point is that you need to understand the bulk mechanism that does it. That's what is the information paradox. So holography kind of by declaration solves it. And in fact, that's the reason why people, like Toft and Susskind thought that holography is a good idea. So an ADS CFT, because the CFT is unitary, we expect it to be, there should be some resolution. So the real information paradox is understanding the bulk mechanism that lets information comes out, or why the horizon is smooth, etc., etc. So those are the kind of questions that really tell you where this thing is. So, but if you assume holography in the hardest sense, then you're kind of solving information paradox by declaration. That's not what we want. We want to stay in the bulk where there are bulk local degrees of freedom, and we want to understand how the information is actually coming out as a sort of more of a mechanical problem. Okay, so that's the question. Okay, so yeah. So by the way, so let me just clean this a little bit. So anything that is older than this, so a black hole that is older than the page time is sometimes called an old black hole. Yeah.
So why are we not using the entire entropy of the black hole for the initial part? For the initial part, we are using the entanglement entropy.
We don't know the entanglement entropy of the. So the point is, so the Page's theorem basically tells you that the coarse-grained entropy is that of the smaller system. So when the black hole is large, the radiation is a smaller system. So that's why we are using the thermal entropy of the radiation as the entanglement entropy of the subsystem, either subsystem.
For the later part, then are we again using Page's theorem, or?
Yeah, we are again using Page's theorem, but now the black hole is small as opposed to the radiation. So we can use the black hole entropy formula. Okay, so always what we are doing is we are trying to compute entanglement entropy, but we are computing a thermal entropy in a suitable limit, exploiting Page's theorem. So in the beginning part, that applies to the radiation, and in the end part, it applies to the black hole. So, and that's what this and this are. And once you have these two formulas, it's just putting them together. That's it. Yeah.
How does thermalization fit into it? You said that.
So all of this is in some sense, okay, thermalization, it means many different things. But in some sense, the assumption that I'm making here is already saying that the full system is at least in some approximate sense thermal. Thermal means, it depends on the time scales involved for various purposes. So for instance, if you look at the black hole and wait till it completely evaporates, the radiation is the most thermal system of all. But that's not the context in which we are working here. We are working in a context where there exists some classes of small operators which will take thermal expectation values if you compute it in this black hole radiation system. So that's what we are calling a thermal state at the moment. So, but it's not thermal in the sense of absolute thermal equilibrium because the black hole is still evaporating. Okay, so that's yeah. Yeah, so the rough idea here is that in the beginning, what happens is that, so the radiation that is coming out is entangled with the black hole that is there, because that's where most of the matter is. Most of the stuff is, okay, most of the Hilbert spaces. So, but once it evaporates and there is most of the radiation, after page time, there is not enough of the black hole left. Okay, so for this radiation to be entangled with the black hole and still remain a pure state. Okay, so if you want the whole state to be pure, then if there is not enough of the black hole, so the radiation that is coming out at this time better be entangled with the radiation that came out earlier on. That's the only option that you have. Okay, so that's why this is a very non-trivial statement. For if you apply to, so for instance, a lump of coal or something, this is nobody ever wrote down the page curve of a thermal system that is burning or evaporating. I don't think ever before, Page did, which is happened after black holes. And the reason is, in some sense, is a trivial statement. It is just saying that if degrees of freedom leave from one half to the other, entanglement entropy will first increase and then decrease. But what makes this interesting is because of the fact that, after a certain time, what you're really seeing is kind of, at this moment, it's still not quite a surprising fact. This is true even for like a coal that is burning. So after a half of, entropy is out there in this thing, the entanglement of the whole system will actually mostly be with the radiation that is out there. Okay, so that picture is still true. But now we can make it, I'll show you that there is a contradiction that one can make. And that contradiction is basically the firewall paradox, the original, one version of the firewall paradox. Okay, so let's write it, what the firewall paradox is. Firewall. So there are versions of the firewall paradox. At some level, I would say that in some sense, Page was So Page's step, the step that Page made is in some sense the most important step after the initial Hawking paper in some ways, because this really shows that semi-classical physics, you cannot escape. People could somehow pretend that information paradox could be resolved by sort of hoping that somehow some quantum gravity magic or whatever could save you. But here it shows that for most of the evaporation of the black hole, semi-classical physics is highly trustable. So you don't know where exactly it is going wrong. Okay, so that's what makes this calculation interesting. In that sense, Page made the information paradox and not Hawking. Because Hawking's calculation is just a statement about 2-point functions of simple operators. Okay, so that is not sufficient to really say that the state maybe could be very complicated. Okay, but here what he is showing is that if so here in some sense he is showing that the state really has to be, somehow we need to have an explanation for this generic state. So this is essentially the question of information paradox. How do you get it? How do you understand it, etc. So this kind of sharpens that problem. So it definitely cannot be the thermal state as one would imagine by doing quantum field theory in the background of the black hole. Okay, so that's why this is the sharpest version of this. Contains all of this other stuff, I would say. Okay, so there is a firewall paradox. It's a very slightly different version was also put forward by Mathur. So but it became kind of like a big deal, or it became a hot topic after this Almairi, Marolf, and Polchinski and Sully kind of rediscovered Mathur's thing but with some one extra bit, let's say. So so I will talk about the version that they are talking about. Okay. So the key assumption is that this is what the main point is in some sense. So what AMS did is that. So as I said, like if you want, we already discussed something before, which is that we assume that the black hole has a smooth horizon. Okay, so this is one of the things that we have, like in computing, for instance, Hawking radiation, we assumed Kruskal coordinates and all that. That's essentially equivalence principle, smoothness, this thing. So the first assumption is that after Page time, if we need a smooth horizon. Smooth horizon basically means it has a very delicate entanglement structure that I wrote down last time. Okay? So smooth horizon, we need to be highly entangled. Highly or nearly maximal is a more correct word. Highly entangled with the interior modes of the black hole. The black hole. So you can think of basically the, in any black hole picture, you will have a region like this, right? So this region should have like a Kruskal-like, the Rindler-like decomposition. That's what this assumption means. Okay, and the state that you're considering here should essentially be Minkowski-like. So, and it should be entangled with respect to the Hilbert space here and the Hilbert space here, and it has a very specific structure. Okay, so that's what this statement means. Okay, so these are, if you want, you can think of roughly as interior modes, these are exterior modes, and they have to have a very specific entanglement structure in order for the horizon to be smooth, and that's what this statement means. Okay, so after page time, if we need a smooth horizon, this is true even before the page time, but you will get a contradiction after the page time is the point. Okay, so this is true at all times. If you want a smooth horizon, the outgoing modes have to be entangled to the interior modes. That's a necessary thing. So horizon, we need to be highly entangled with the interior modes of the black hole. So that's the first observation. And the second observation is basically, now we really need, so this is after page time is sort of incidental here. But the second statement is that after page time, because of the argument that I just made, and in fact page's own calculation, what we are finding is that this here, the after page time is very important. After page time, the outgoing modes, again the outgoing modes, have to be nearly maximally entangled. Also with the early radiation. Okay? So essentially what we are saying is that the outgoing modes, the Hawking modes that are coming out of the black hole after the page time are simultaneously highly entangled to the interior modes of the black hole, as well as the early radiation modes that left the black hole long time ago, presumably in some part of this slope here. Okay? So, and this is in violation of a principle in quantum information called the monogamy of entanglement. So we will actually have one lecture at some point discussing various, quantum information like facts, mid-decomposition, this, that, etc. But today I don't want to get distracted with it, so we'll just take it as a fact. Okay, so after page time, so this basically means that the outgoing modes, let me call it the H outgoing modes, is simultaneously maximally entangled, maximally or near maximally entangled. Even highly is enough, okay? Highly is enough. It's not very important. Did I do something to the thing? It's okay? Okay, so is maximally entangled with both Hilbert space at the interior of the black hole and H early radiation. Okay, so this is the problem, and this is in this is in violation of this is a contradiction. This violates monogamy of entanglement, which basically says that a state in the Hilbert space can at best be maximally entangled or highly entangled with some one system. You cannot be both entangled with one system and some other system at the same time. So violates monogamy of entanglement. And this is a fundamental property of quantum mechanics, so there is no way around it. Okay, any quantum mechanical system should satisfy it. Okay, and that's basically, so the proposal of AMPS was that maybe the most conservative resolution to that question is that you just sacrifice the smooth horizon. Okay, so because in order for unitarity to come out, you definitely need this, the entanglement, so unitarity of the system to finally come back to a unitary, pure state at the end of evolution. You need the Hawking radiation after the page time to definitely be entangled with stuff, the radiation that came out earlier. That we cannot avoid. So maybe the most conservative thing is that old black holes may have firewalls. So this was the proposal of AMPS. Okay, so that's firewalls basically means you are breaking the entanglement structure of the horizon, and you essentially have, you have what they are calling, that's basically the thing that we computed. We computed an energy density and we computed it, and then we found that it blows up as like basically the UV cutoff of the effective field theory, right? So, and that claim is basically what is called the AMPS firewall. So, but there is, but there is an implicit assumption here, which is that it assumes that the interior modes of the black hole after the page time are distinct from the radiation that left the system. Okay, which seems like a very natural assumption, because the radiation that left the system is probably light years, not even light years, billions of light years away. But, I mean, not even billions. I mean, the time scale of this for an astrophysical black hole is humongous. It's bigger than the lifetime of the universe, much bigger. So, which means that this radiation that has left the system is, if we are living in a flat space black hole, if you're living in with a black hole in flat space, let's forget for a second that we are living in a cosmology and all that. So, if you are living in flat space, this radiation is like, by that time presumably trillions of light years away. But the claim is that one way to salvage the smooth horizon is to declare that radiation is actually the same degrees of freedom as the degrees of freedom inside the black hole that is left. Okay, so and this you can think of. So this is something that, for instance, so this at this point we are kind of diverging into people have different opinions, etc. So I would say that the conservative opinion at the moment, at least, is that this is true. Okay, so that the radiation, the early radiation, is where the interior of the black hole sits. Okay, the interior of the black hole is in the Hilbert space of the early radiation. So you can think of it as a very sharp form of, this is a form of holography. So this is essentially, and this piece is, I would say, what, for instance, the people who believe in fuzz balls and so on, there is this idea in string theory that black holes, black hole microstates have close off, cap off before the horizon. Okay, so if you want to look at a microstate of a black hole, because black holes have thermal entropy, which means they're comprised of, there is a state counting entropy associated with them. In the same sense that log of omega is entropy for Boltzmann, right? So if you have a thermal entropy, you can count the states and get an entropy. And so what are those states? Those states are, in string theory, once we have full control on it, we will call them black hole microstates. Okay, so that would be so in string theory, we know in some cases that you can actually compute this entropy by state counting by using some trickery. Okay, so there are cases where we know how to do it. But the point is that this observation is the question of fuzz balls. I'll just say what fuzz balls are very roughly. So fuzz balls are this idea that in the microstates, in the gravitational description of these microstates, they close off before the horizon, and these individual microstates do not have a smooth horizon. Okay, so the proponents of fuzz balls, I think, do not believe in the statement that I said just now, that the radiation which is living far away is not encoding the interior of the black hole. Okay, and the reason is, if you do semi-classical gravity, there is no hint of, in that sense, there is no immediate hint of holography, right? If you do perturbative string theory, or so holography is something that was surprising. So, and that I think is a surprise that they are, at least, I think that's the place where they would depart from this conventional, so this is what I would call conventional wisdom at the moment, even though it's hardly conventional. That the radiation at far away basically encodes the degrees of freedom in the interior. Okay, so this is it has been around for a long time, and so there are various statements of this kind. So the point is that, but I also want to give you another possibility. Fuzz balls essentially are a way of, fuzz balls are basically saying that firewalls are the right answer. Okay, so that the horizon, there is, firewalls, Amps wrote the paper after Mathur, but Mathur was saying fuzz balls for, probably a decade before that. So, the idea there is that the space-time closes off before the horizon and there is no smooth horizon. So it's essentially another version of, that's the main assumption of firewalls. You can call it whatever you want, but at the end of the day, that's what it is. Okay, so that's the picture of any general knowledge stuff that I should say, other than this. Yeah, so this is a type of non-locality. So the words that you can use are non-locality. Okay, so holography is, let me call non-locality. It's probably slightly better. Okay, so there is some kind of extreme form of non-locality that happens in black hole physics at late time evolution, is what it looks like, at least at the moment. Okay?
Non-locality means the field of it is not communicable.
Well, I mean, it actually, so like it is, right, it is, at some level that is true. So yeah, you can also think of it more prosaically as somehow, if you have strings, for instance, have some amount of non-locality. And I don't think we have fully understood the full extent of locality of string theory. So if you have strings, they're not point particle interactions. Strings can interact even at a distance because they're finite size, right? So that's one way of thinking about non-locality. So yeah, but I mean, yes, you're right in the sense that if you think of in terms of field operators and so on, it's essentially a statement that things don't commute exactly at macroscopic distances. So, and it's something that people have thought of even before because of string theory. Okay, in fact, holography came up as a way of escaping this. Okay, so but in this particular context, I think people are still surprised that this may be true. I mean, if it is true, it's still kind of in the, I think it is becoming the conventional wisdom, but I don't think it is still completely settled. Okay, any questions? Yeah.
Holography states that the radiation has just come out very early, enforcing.
I'm not saying that holography says that. I am saying that this is a type, you can think of it as some kind of holography. Because degrees of freedom there also capture something that is somewhere else. That's all I'm saying. I'm not saying that holography, this is not quite conventional holography. Conventional holography is, it's basically saying that, we'll get to it. Yeah.
So it's like saying that you can build the H interior from H early, something like that.
Yeah, the H interior is constructed from these two Hilbert spaces are essentially in some sense equated. That's what you're saying.
But like, if there is a firewall, then the outgoing thing won't be maximally entangled with interior.
Correct, yeah. So if there is firewall, so this is a way in which we want to avoid the firewall. So we want to say that the horizon is smooth, and if we want the horizon to be smooth, because the first assumption that I wrote down there is basically coming from HO is entangled with HI, right? So that statement is directly a consequence of the smoothness of the horizon. So, and I'm saying that, but we also need from unitarity and page curve and so on, this also has to be entangled with this guy. Okay, so but then both of them are simultaneously entangled and they are nearly maximally entangled. That cannot be the case because of this general principle of quantum mechanics. So, and then we are saying that, okay, so one way to say that is to break this assumption, that is the firewall. And another thing is to say that this is, these two Hilbert spaces are the same, which is, you can think of it as holography of some form, some sort of generalized holography, or more commonly it's called non-locality. Okay, so, yeah.
So if we are assuming the radiation that came out after the page turn and the interior modes as the same part of the system, that's how we are avoiding the monogamy of attack.
No. So this and this has to be entangled. It's not the same statement that this and this are the same.
No, not that.
Yeah?
Early radiation and the later radiation.
So the later radiation. So this and this has to be maximally entangled, and that's coming from page curve, because otherwise the information won't come out. Okay, that just comes from this general argument that there has to be enough information in the late radiation, and so unless otherwise the page curve won't turn around basically. So, and that's where that is coming from. So that I think is essentially unavoidable because Page's calculation is essentially unavoidable. For any system it's true if you assume unitarity. Any thermal system which is radiating, there is no way to escape it. But this one on the other hand, it's somehow up to us. So that's why AMS kind of came up with this thing that maybe firewall are the more conservative assumption. And but of course, so if you don't want to be conservative, then this is another possibility. And there are reasons to think that in gravity, that such forms of non-locality may be true. Okay, so but of course the point is that it's not immediately accessible to bulk effective field theory. So bulk effective field theory, somehow everything looks local. Okay, so that's the remarkable thing about bulk effective field theory, because it is essentially like general relativity, it looks like everything is propagating locally, there is no magic. But holography is saying that somehow the stuff that is sitting here is actually the same stuff that is sitting there. Which, if you really believe in holography, even now, in our universe, it is true. Holography is I don't think the public has really understood how crazy of an idea holography is. People talk about quantum mechanics or general relativity or whatever. But on the other hand, holography is insane. You know what I'm saying? So it's like basically the statement is that all the degrees of freedom that are sitting here are somehow captured by the degree, some fictitious or otherwise screen sitting at the infinite, at the infinity in space-time. At least for certain class of spaces. Okay? So that's what holography is saying. So if you are willing to buy that, then this is like, small pittance. It's not a big deal. So this you can buy if that is the case. So and for at least in other contexts, so I don't think people have ever bought this unless they had very strong evidence for holography in other settings or non-locality of the kind that smells of holography. I don't know whether I would really call this holography, but at least it's very similar enough to holography. Okay, that there is some degrees of some system sitting here which is described by what presumably is a system sitting somewhere else. Okay, so yeah. Okay, so I think so let's talk about a couple of more things and then we'll close the day. So one thing that I want to say is, so that's kind of like that, that's our first introduction to sort of firewalls, genuine firewalls, and not just the, the Minkowski firewalls that we were playing around with last time. So, so now we want to talk about, so let's see so one thing I kind of, this is kind of an important thing and I think it is not sufficiently emphasized often, is this notion of typical state. Okay, so we already talked about typical states in various contexts, but I think it is probably something that is still not completely understood, I would say. Or at least the typical state is, of course, some generic state in the Hilbert space, but what its relevance is for black hole and the smoothness of horizon and so on. Okay, so let's consider this, let's say that we form a black hole. Okay, so we form a black hole by starting with some gas or photons or whatever, like a shell or whatever, that kind of thing. So it doesn't even have to be, so this means that its energy is going to go like this. All of this is just Planck's law, by various forms. And this will be V times T cube. So the V is sitting here because both energy and entropy are extensive quantities, and T4 and T cube basically it just depends on photon gases in 3+1 dimensions. Okay, so this is all of this is just Planck's law. So now what we can think about, so this is what you have for a gas of photons or gas of whatever it is that you're going to collapse to form a black hole. Okay, this is what it had initially. Okay, so now let's assume that you made a black hole by starting with this object, this system, and you contained that within a volume which is, so let's say you started with an energy equal to m, which is the mass of the final black hole. Okay. And you put that, if you put that in an area or a volume of this much, you will basically form a black hole. Okay? So if you do these two things, you will basically get a black hole. And from these formulas, it's a trivial exercise to show that you will find that this goes as area of the black hole to the 3/4. Okay? So this is, you can just check, area is basically m squared. Okay, area is m squared. So if you put all these things together, you will find that this goes as this. So what that means is that the entropy contained in a gas of photons contained within the Schwarzschild radius when it forms a black hole is not as high as the entropy of the black hole. Okay, so the entropy of the black hole is higher. So that means that when you form a black hole, you're not forming the black hole in a typical state in the Hilbert space, because the Hilbert space size is basically e to the s. So once a black hole is stabilized, this means that this goes as e to the a. Okay, so for instance, a black hole which is like, which once it has formed and it is thermalized and a black hole has, so it also says in some sense that even after you form a black hole, there is some form of evolution happening inside the black hole, or in some microscopic degrees of freedom, which general relativity maybe is not really sensitive to. Okay, there is some form of evolution still happening, and that's what this means. This means that if you form a black hole, at least from outside it will look like a black hole, but its entropy, if you just start with this much of stuff to form a black hole, it's not quite enough to saturate the Hilbert space. So note that this is a to the 3/4. You might think that, it's only a little bit smaller than a, but it's the entropy, the Hilbert space size is e to the s. So which means that this is, a very tiny part of the Hilbert space of the microstates of the black hole. Okay? So this is what is called a quick collapse black hole. So a quick collapse black hole, or at least, so at least in the early parts, let's say in the beginning parts of this picture here, we expect, So that region, once the black hole is formed, I mean, from outside it looks like its area is this much and so on. So there is a distinction to be made between black holes, which are just formed, sort of quickly, and we will fix some time scales eventually. So, and the black holes which are somehow old veterans and are sitting here. Okay? So these are in some sense closer to typicality. Okay, so the question of when exactly typicality kicks in is a complicated question. We will get to it, maybe at the end of the lectures. Yeah.
Like old, you mean eternal or they have
No, these are all evaporating black holes, right? So there is no. I'm not talking about eternal black holes at all. So first of all, the eternal black holes in flat space are a fictitious entity, right? That's semi-classically classically you can draw the picture of the Kruskal diagram. So it's not really like they will eventually. So it's not clear what their full, because Hawking radiation will definitely make them lose mass. So they cannot be eternal in the sense of the Penrose diagram. Once you have, Hawking radiation. But in ADS, and which we will get to in ADS, when we talk about ADS black holes can be eternal. So then this question of which states are typical, etc., are questions which are still being debated. Okay? So this is what I wanted to make one statement, which is that in some sense black holes which are formed by quick collapse or black holes formed recently, in some suitable sense of recently, are not typical yet. Okay, so so we will come back to that because that's yeah. So one final thing I'll say is the idea of black hole complementarity. So black hole complementarity is again sort of a quasi-philosophical idea. Let me give you, so let me actually give you, so this is an interesting observation. So this is the entropy. Essentially this is the entropy of quantum fields which are contained inside the size of a black hole. Okay, so that's what this is. Okay, so and I don't have time to cover it, but this observation and the fact that this doesn't quite saturate the Bekenstein-Hawking entropy has a very interesting connection with the cosmological constant, and that's called the Cohen-Kaplan-Nelson bound. So it is, if you are interested in particle physics or cosmology or cosmological constant and so on, I suggest that one of you can take this as a topic for like writing up. I don't have time to cover it, but I think it's a remarkable connection, and it is one of the things that I find like maybe closely related to the, maybe powerful enough to solve the cosmological constant problem. Okay, so you can go Google this. They have their paper. I think it has like 1,500 sites or something now. So, but it's an interesting idea, very closely connected to this observation. That if you put a quantum field theory or Planck radiation in a size of a black hole, it doesn't saturate the entanglement. The Bekenstein-Hawking entropy. So that observation, from leveraging from there, they talk about how one might be able to make an argument for why the cosmological constant is small. Okay, it's an interesting argument, and I think it's probably correct. So anyway, right. So this is one topic. So one of you can take it. So one topic. So we have so far I think given like 4 or 5 only so far, but you can pick some of your own if you like. Okay. So so let me also give you a small exercise, which is again related to this question of typicality, which is that compute, it's an easy exercise, compute the final entropy of the Hawking radiation using Stefan Boltzmann law as the radiation is coming out. Okay, so the black hole is sitting there. It starts with the black hole of mass m, starts radiating. So, and when the radiation is coming out, when the mass of the black hole is m, you know what its temperature is. And once you know the temperature, you know what the entropy is for radiation. So you can integrate it over the lifetime of the black hole and compute what this is. Okay, and you will find that this, so you will get some answer. And the claim is that, so in this entropy, compute the final or total entropy more precisely. This entropy is greater than the SBH that you started with, the Bekenstein-Hawking entropy that you started with. So this you can check. Okay, and that basically says that at least for evaporating black holes, these are not states that are typical in the sense in the let's say in the canonical or microcanonical ensemble. Okay, let's call it microcanonical ensemble because the temperature is changing. Okay, so in the microcanonical ensemble, let's say you are working at a small sliver of initially, in the final state system has higher entropy than the initial state system, and that's why the Hawking radiation happens, because it's thermodynamically allowed. And then it also means that black holes are not typical, at least evaporating black holes are not typical in the microcanonical ensemble. This is also an important fact. Okay, even though they are thermal states, they are not typical states in the microcanonical ensemble. Okay, so yeah, so those are two comments. Now I will go to black hole complementarity. So, and it's kind of like a okay, so black hole complementarity is basically just the statement. It's just one picture essentially, or at least one version of black hole complementarity. I am going to, yeah, so I think we have seen pictures of this kind before. So there is a collapsing shell, and yeah, so there is, so these are the Cauchy slices in the space-time. Okay, Cauchy slices means some equal time slices. So the reason why this is interesting, or it's worth looking at, so this was first done by Susskind and Torlashis and Aglom. At least, in this version, I think Aglom may not be there. But yeah, so the point is that, so the basic observation that Susskind and Torlashis are making is that, Hawking radiation, if all the information comes out, right? If all the information comes out, there is a sense in which it looks like there are things happened inside here. There is, there is information that is here that also is available here at very late times. Right? Whatever fell into the black hole, presumably, is what is getting evaporated at late times. So at very late times, there is information about whatever happened inside that is available here. Okay? So, and here on the other hand, when you throw something into the black hole, or the shell that formed the black hole, it looks like this guy here, if you are here, this guy will basically know about the initial state that you started with here. But this initial state information is fundamentally also available at late times here. Maybe, like if I draw this Cauchy slice really close to the boundary. So this is, like here versus here, it looks like there is information about the initial state that you started with here to form the black hole is available definitely here because it is just the infalling trajectory. But because Hawking radiation presumably purifies, is taking the information outside of the black hole, at least if you wait long enough, presumably it is there also here, right? So, and this can in principle, so this is at least superficially it looks like what is called a violation of something called the no cloning theorem. So this is another, quantum information thing. So along with okay, so violates no cloning theorem is if Hawking radiation takes out all the information, and if this information is there here as well as here, it looks like the information about the the original state of the black hole is available in two places, in two places, or there is two copies of the state somewhere available. So this is sometimes called, and this is, something that you don't expect to happen in quantum mechanics. In conventional quantum mechanics, you cannot have that. So no cloning theorem along with monogamy of entanglement, etc. We'll talk later. So it's another fact. So, and the reason why is the idea of Susskind and Torlashis and the black hole complementarity is the idea that no single observer can actually measure both this and this. So because let's say somebody who is sitting very late here and tries to measure, collects enough Hawking radiation to reconstruct the state and decides to jump into the black hole, he will never be able to get here. Okay, so this is so far out in the Penrose diagram that he will hit somewhere here, and this guy has no causal accessibility with this. And you can play around with some pictures of this kind and convince yourself that this is true. Okay, and that is true. So if you have, I drew this Cauchy slice in some way, but it cannot be violated basically. So this is a geometric obstruction to no cloning theorem, And so this is sometimes called black hole complementarity. So the only thing you don't really need to think of, so you basically what you need is the fact that different observers don't simultaneously are not able to basically compare two different observers. Any individual observer is not going to find a violation of no cloning theorem. Yeah, that's a better way of saying it.
How does causal inaccessibility of those information proves inexistence of those information?
No, it doesn't. It doesn't. So the claim that complementarity is making is that this is the extent to which we should demand, no cloning and quantum whatever. So the statement is that, like another way of saying the same thing is that maybe, you can choose to sacrifice various things. I mean, I guess one way to, so one way to say that is that the idea that this Cauchy slice is somehow, is a good way to describe time evolution of a certain kind is not the most useful way to describe it. That's one way to look at it. But you're correct that there is, so it's again the question of uncertainty principle type of thing, right? Whether, whether is there, if the tree falls in the forest and nobody's watching, is it really falling type of question. So that's why it is called complementarity. Because these two observers have complementary descriptions of that information, but they are not going to be able to compare it. Okay, so that's the way in which no cloning theorem is sort of surviving. Okay, so yeah, but anyway, I mean, this is not really like complementarity is more like a philosophy, or I don't know. It's not like.
It's kind of like computationally restrained. Like we can't access that, so it doesn't exist.
Yeah, I think you can. There is actually a version of this which is a little bit tighter and kind of in line with what you're saying, which is called the Hayden-Preskill argument. So there they make it a little bit more precise by saying that you cannot do this computation, you cannot extract this information in a certain amount of time, etc., etc. So
it shouldn't exist, or it might not exist.
So it's like it depends on what you like. These are all low curvature regions in space-time. Right. So whether you want to, if you are a God-fearing effective field theorist, you would say that this Cauchy slice is completely well defined. But then the question arises, what kind of these are questions which are kind of philosophical, right? In the sense that in quantum mechanics, you always have to have some kind of an observer. Without that, you can't really make a sufficiently clean statement, or So whatever you want, So I don't know. I mean, I'm just saying that, this is what complementarity is. I'm not saying that it is, anything that you don't want it to be. But it is, this is essentially what it is. That two observers exist, but they cannot, they cannot possibly confirm that cloning happened between each other. So that's not possible. That the causal structure of the space-time forbids it. And so one reason why people sort of like it is because, maybe this is another way of saying it, which is that the question, most of the things that we have access to about black holes are basically from outside, right? Because we are, all the things that I talked about very roughly have like an S matrix kind of flavor. So things are scattering out, you're looking at infinity, that kind of thing, okay? So we are all doing things with, in some sense, the asymptotic observer is the key person in this business. But, so the question is, whether what happens to a guy that falls in, that is something that you can easily ask in classical general relativity, because the coordinate system is well defined in principle of equivalence and all that. But here, it is not very clear how to make sense of it, because we don't have an immediate way of connecting the infalling observer. I don't think we understand the infalling observer at all in quantum black hole. We don't understand it at all, okay? So there are various things one can talk about that, but the point I'm trying to make is that here, if the infalling observer had to be a real entity, let's say it was well defined, then one would definitely need this kind of a black hole complementarity to salvage no cloning theorem. That's the statement, another way of saying the same thing. Okay, so but if there is no smooth horizon, etc., then already the infalling observer is not there, right? So if you want smooth horizon and you want no cloning theorem to be true, then you need various things of this kind. So this is the sort of idea.
When you say that the black hole is completely irreproducible, then what information is inside there that we want?
What information is where? No, this is just the information about the initial state. So the idea is that there was a guy who knew the state of the shell that he started with, and he just jumped in. So he'll just retain that information. So that's what this is. You're not trying to get that information from somewhere else. It's just that this is like Hamiltonian evolution, if you like, or of this observer. So, but the point is that this is the non-trivial part. This part is, it's just standard evolution. But here, when you say that Hawking radiation basically carries information away, right? If it carries information away, then there is a question that you might have an observer sitting here who can in principle collect it. Of course, this is a complicated question. It's like even for like a burning piece of coal, we cannot extract all the radiation and then reconstruct the initial state. That's, it's an impossible problem. So, and there is ways of quantifying it. And here it is essentially the hardest problem in existence. So, and the question is, but let's assume that it was possible. Then, there is this issue of, it seems like the state has been copied twice. So how do you get past that? And essentially, complementarity just gets out of it by declaration. Okay? So just says that, okay, these two guys cannot interact with each other, and that's good enough. Okay? So,
what are the four people of ants?
Almairi, Marolf, Polchinski, and Sully. Yes?
I think such can also make the statement that whether the horizon is smooth or it is a firewall also depend on the observer, whether it is really falling or accelerating, something like that.
Well, I mean, the observer, I don't know. I mean, I see the property of, so I mean, there are, like for instance, the probe that you're using to measure smoothness of the horizon matters. Okay, so but like there is a geodesics we assume exists as in some classical limit of quantum field theory, right? So those geodesics are like, but there is the hard thing in some sense is to characterize infaller in a kind of a useful kind of diffeomorphism in coordinate invariant kind of way and so on. So those are the things that make things difficult. Especially, how do you characterize a state that is going in or a infaller that is going in? Let's say if you're an ADS-CFT, what will be the boundary description of it? So these kinds of questions are always, they have various issues.
One more thing, like the observer that is like extracting information from the Hawking radiation.
Yeah.
And then you are saying that it cannot. This is the observer that is already inside.
Yeah. Because the radiation, essentially the statement is that if you if the shell that goes in basically hits the singularity very quickly in some sense, and the radiation, if you want to wait, if you have to get the radiation out, right, in order to reconstruct the original state of the black hole, you'll have to wait a very long time. So, and because of that, if you wait long enough to get that information and then jump into the black hole, then you don't have, the original shell would have already hit the singularity by then, essentially.
So it is not related to the fact that some of the interior of the black hole is like expanding.
It is completely related to that, right? Because here also, like this, essentially from the perspective of the guy who has jumped in, that's what is happening. Right? So one other way of saying the same thing is that, see, like let me draw one picture. So so let's say you have you have a word line that hits the singularity. This is the singularity, right? So from the perspective of the guy who hits the singularity, these regions are causally inaccessible. So the point is that this guy, it's in many ways it's like a cosmological horizon. So the word lines which were living here, all of them have left the past light cone of the guy who is hitting the singularity. So in that sense, yes, all of these are kind of spreading away from him. He doesn't have access to them. He will, like it's the same thing that happens in an expanding universe. So if you have a geodesic or an observer sitting here and an observer sitting here, like all of the galaxies are going to leave our horizon in the future, right? In that same sense, the same mechanism, essentially what it is here, because there is but here it's happening because of a different reason, because, in the case of the expanding universe, okay, so the universe is expanding, accelerating expansion and so on, so the geodesics are going to leave the horizon, the cosmological horizon that you have access to, but here it is happening because you have a future, your future is finite. So you're getting truncated at some finite time, and because of that, there is a sense in which all the geodesic guys that are living were in your causal past. By the time you hit the singularity, they would have all left. Okay? So yeah, so it's something roughly similar is what is happening here as well. So if you jump in here, your future causal wedge will be like this, but here it is like this. So these two don't intersect. It's very similar.
Can we say every free falling observer has finite time? If there
Every infalling observer. Yes. Yeah. So if there is, at least in classical general relativity, so the infaller in quantum, gravity or quantum mechanics is incorporated. It's not clear. It's not clear in the sense. I mean, how seriously should one take infalling observer is not completely clear. So yeah, but what I'm saying is that yes, if you in classical general relativity, the proper time to the singularity is finite. So you will hit the singularity. You know what I'm saying? So that's the picture. Okay.